I'm really, really excited for this talk. So I looked at this paper a while ago, Jason, and when I saw when I saw what you guys had published, I was like, this is crazy. This is going to be awesome. So you guys today, you've heard a lot about LLMs and making LLMs accessible and all of these different things. Well, I think you're about to hear one of the most interesting research pieces of research to come out this year. And the most compute-heavy piece of transform models like LLMs is the number of matrix multiplications that have to go into each call. And this is a huge blocker to LLM adoption across the board, whether you're going to be doing edge compute, whether that's GPU availability, or simply through raw power consumption. And so that's why I'm super excited to have Jason Eshraghian here today to talk about new research that could be a breakthrough for this kind of LLM adoption. Jason, I'm going to take your slides to the stage and you can take it away.
Awesome. How's the audio? Can you hear me all good?
I can hear you just fine.
Thanks for the invitation. I appreciate you having me out to talk about these matrix multiply free LLMs. For a bit of context, I remember seeing Jan LeCun tweeting about how we need to divest, or academia needs to divest away from advancing LLMs because industry's got it covered with a hell of a lot more compute. So it was pretty cool when we kind of came across this, what I feel like is a bit of a big breakthrough, because we're able to get some seriously solid performance with very limited compute. Of course, more compute is always nice. It's always nice to be able to take these techniques that do work with limited compute and just seeing how far they can be pushed. So that's where we're at the moment. But without further ado, let's dive into this preprint and see what it's all about. So for context, it's the first billion parameter scale matrix multiply free model to achieve language generation. This is a very high level overview of, self-attention on the top left, the operators required for the matrix multiply free approach on the right. And so we're going to break this down very briefly in order to get a sense of what's going on. At a kind of an arm's length view, the things that we did were threefold. So firstly, we took that bitnet approach. You might be familiar with Microsoft's work in ternarizing all of the parameters in an LLM and still getting really nice performance. Ternarize as in setting or constraining your weights to +1, -1, and 0. And in that case, your multiplication just becomes assigned accumulation, right? That makes sense, right? If you multiply some activation by +1, it's just the same activation. If you multiply it by -1, then it's just the negation of that activation. And in custom hardware, you would just kind of bit flip the leading bit to represent that. And if it's a 0, then it's a 0, right? Which just blast away all of the bits of your activation, replace them all with 0. So the point is, in hardware, you're able to implement ternarized operations as just signed accumulations. You no longer need a multiplier to be instantiated. Then the second thing that we did here was replace the attention map. So historically, self-attention is used to do some sort of token mixing in order to understand the relationship between words or syllables, or more generally tokens, and how they relate to each other across long sequences. That is a big part of why language models have been able to achieve the performance that they have been able to achieve, and why they can remember something you said at the start of a paragraph several pages later, or many pages later in the case of Gemini. With BitNet, they did this ternarized approach, but the outputs of their what they call bit linear operations, or bit linear layers, still requires some outer products and matrix multiplication with non-ternary parameters. So while they're able to do some really good stuff with the amount of high-level memory or DDR access that they might need there, there is still a matrix multiplication, and for reasons I'm going to show you in a moment, that requires a significant chunk of low-level memory or caching. So we went ahead and replaced that with some other matrix multiply free approach. So we just replaced it with the linear gated recurrent unit. and things work pretty well. Now, where BitNet left us was with this kind of theoretical model, which unfortunately wasn't released, but hopefully we've kind of compensated for the absence of BitNet being open source in this work. But they left off with a call to action and said, hey, this model doesn't work as efficiently as it could otherwise on a GPU versus some custom hardware implementation. So we call on the hardware engineers of the world to go ahead and optimize low bit width operations and more lightweight LLMs. So yeah, we kind of took that up on ourselves and built our own FPGA implementation of this model as well. And as a result, we were able to run this model at 13 watts with human readable throughput. So just to kind of like wrap this up, these first two things are what enabled this matrix multiply free language model, and the custom FPGA implementation actually makes it useful, right? Granted, it is of course useful to still be able to have the knowledge that a ternary LLM is going to work effectively, but actually deploying it is something else entirely, and gives you something really concrete to work with in silicon. So with that being said, let's just kind of take a very high level view of what self-attention is. It basically just involves, yep, excellent, you can see my cursor. It involves parsing this token embedding. It splits off into 3 parallel dense layers, which generates your QKV outputs, your query key and value outputs. Your query and keys are going to be mixed together and then somehow used with your V matrix or V vector. And as a result of that, you ultimately generate one single output. Now, in the background of all of this, you need to store the outputs of your key and values, or you need to store your key and values because they're going to be used in your next step, right? So once the next token gets passed to your model, so we'll denote this as x of t equals 1. This could be x of t equals 2, where the top part of our operations are going to be operating on the first token, then bottom row is operating on our second token. Then we need to be able to do the exact same operations, but we need to keep a perfect history of our k and v values. And then so that's called the kv cache. And the kv cache is going to increase with an increasing context window. So that's a result of having to do matrix-matrix multiplication. This is just a more sequential way to execute mat-mat-mult. Now, on the other hand, and so yeah, you just keep doing this until you've exhausted all of your inputs. So on the other hand, this matrix multiply free approach is quite different. There are some parallels here, but let's break it down. It starts off seemingly the same way. We have our input embedding. We're going to take our input vector, embeddings, tokens, whatever. We'll pass them through a linear layer, but this time it's a ternary linear layer. And as a result of being ternarized, any linear layer or any linear dense operation is just, like I said, converted into a signed accumulation. So replacing vector matrix multiplication with signed accumulation. So from a software standpoint, if you were to code this up in Python, it might feel like there is no difference. From a hardware viewpoint, you can get rid of all of your multipliers. So again, you probably want custom hardware to be able to exploit something like this. So you end up with a set of outputs from these ternarized operations. And then what you do is the following part, the way that this is all color coded, hopefully to make things make a little more sense. We're doing a couple of sigmoids and this tau operation, which represents a silu. We're going to end up operating on these using this linear gated recurrent unit, which is visualized here. I should mention, so this GLU, it's basically doing token mixing in the way that self-attention is meant to as well, just with cheaper ops. We tested a variety of token mixes, including Raku 4's token mixer. It just so happened that this worked the best. And as a matter of interest, The Raku4 token mixer, which we report this in our appendix kind of as a negative result to hopefully avoid the research community from wasting compute resources doing experiments that we've already run and didn't end up working as well. The Raku4 token mixer has a series of exponential operations, some divisions, basically a bunch of transcendental functions. So given that added complexity, you'd think it would work better. It did not. So this is what we used. After a set of these Hadamard products and sigmoid operators, all we need to do now is cache a single hidden state. That hidden state here does not grow with context length. We're not doing any map mold. We're not doing vector matrix mold. This hidden state doesn't need to grow. It just kind of gets projected to your next sequence step, and you just do the operation again. And so we've seen that this linear GRU can do really well up to context windows of 2K and thereabouts. And going beyond that, as far as I'm aware, it remains to be seen how well it can handle longer context windows. So we're very interested in kind of extending these experiments and seeing what needs to be done to keep pushing, I guess, these state space class of models or linear attention-based models towards those ridiculously long context windows. So of course, there is probably going to be some level of trade-off by discarding that KV cache and doing something far cheaper. As of now, as of the 1K, 2K context, we're still good. We seem to still be getting performance on par with self-attention, so that's nice. So I don't know, a logical next question could very simply be, all right, we went through all of this effort to ternarize or to build this matrix multiply free LLM. Why don't we just ternarize a bunch of things that already exist, right? Can't we just ternarize pre-existing LLMs and get similar performance? No, the short answer is no. We see on the y-axis loss and on the x-axis the number of tokens that have been trained. We use Transformer++ in the blue line as a baseline for comparison. For a few reasons, it's the backbone of a lot of state-of-the-art models, including Llama 2, Llama 3, Mistral, and a few others. Of course, they extend it and do some more fancy tricks and whatnot to make it more effective. But it is still the backbone. And much of the recent literature on linear transformers, so we're talking Mamba and GLA, they've also used Transformer++ as the baseline for comparison. So we kind of followed that mantra. So with that being said, what have we actually done? I've been alluding to how perhaps this model is only good for custom hardware implementations, but we still have to train this. And I should mention this caveat that this matrix multiply free approach is during inference only. For training, we still have to do matrix multiplies and whatnot. We're operating with BrainFloat 16 numerical formats. So we still have vector matrix multiplication during training. Of course, I think that is still valuable because you train a very solid foundation model once, and then you have a billion requests per day that only need to run inference on that model. So I would argue that inference is probably the more the thing that is going to cost you more when you have such large scale demand. Now, having said that, we still ran a set of optimizations for GPU. And as a matter of interest, so what we did was we fused a set of the kernels to accelerate training throughput. This was actually done out of necessity, and it's the only reason why we met the Nurix deadline. I think we finished our 2.7 billion scale parameter model training run several hours before the submission deadline, and it was basically because we were forced to do some CUDA level optimizations to actually enhance training. But as a result of doing that, we were able to use 2x less VRAM and accelerate training by this factor, so 25% less training time. These plots here are just kind of showing you what a vanilla bit linear layer looks like and what this fused bit linear layer looks like. So just a bit more context, fusing the ternary linear layer along with the root mean square norm, which just kind of normalizes the output vector of the ternary operations. So on the left, this plot represents time versus batch size, and on the right, memory versus batch size, the fused approach is in orange and naturally does considerably better in both cases as your batch size increases. Then secondly, we also wrote our own custom CUDA kernel to accelerate inference, basically to just better leverage the ternary weights that we're using along with 8-bit integer activations. In doing that, we then also get GPU benefits for inference. And so we were able to get 10x less VRAM during inference. So this plot here is comparing the VRAM that uses Transformer++ against that with matmul free. So that's on the left y-axis, and on the right y-axis, we just have the same thing with latency. So in this case, lower is better, lower memory, less latency, so all is good. The x-axis sweeps across a variety of model sizes. We've gone up to 13 billion. Of course, I should mention this 13 billion relies on randomly initialized weights. So this has not been trained. We're just running the model, assuming that we are able to scale up to that parameter size. So then following that, the question kind of becomes how scalable is this, right? Something's got to give whenever you're winning performance or efficiency. It's there's always something that we can do better, or there's always something that you're going to lose. So let me break this down for you. This top graphic here is taken from a preprint from scaling laws for neural language models from OpenAI. Let's start with this plot in the middle. It shows the test loss almost linearly decreases with an increasing data set size. They've given this curve fit as well. I guess if 0.095 was 0, then it would be, I guess, perfectly linear. The plot on the right shows something similar, but instead of the number of training tokens on the x-axis, the number of training tokens is fixed, and instead the number of parameters in the model is increased. And then the plot on the left is kind of like the product of these two things, the product of the data set size and parameters, and that gives you PF days, which is petaflop days. So it's more about how test loss drops with increasing compute. Of course, crank up your model size, you need more compute. Crank up the number of training tokens, you need more compute. So what is noted here is that for optimal performance, all three factors need to be scaled up in tandem. So empirical performance has this power law relationship with each individual factor when it's not bottlenecked by the other two. So inspired by that, we explored how this scaling law functions with our model. So down on the bottom here, we see the y-axis, we have loss, and on the x-axis, we have flops, floating point operations per second. And you'll notice that these dashed lines kind of come in clusters of two. So one of these is our model, the other is just going back to the Transformer++ that is not turnerized, so a BrainFlow 16 implementation of Transformer++ that we retrained ourselves. The lowest two curves are the smallest model, the 370 million parameter versions of Transformer++ and matmul free. And then the largest two, as you kind of move to the right, which requires more flops to train, are our 2.7 billion parameter models. So you'll notice that in all cases, these two models, these pairs of curves are really quite close to each other, and they get closer and closer as the model scale goes up. And so then you keep training. The dark line is what we actually trained, and then the faded transparent line is our scaling law projection. So once you hit this region between 10 to the 22 or 10 to the 23 flops, then the two are expected to converge. So that's all well and good. A valid concern could very well be that this linear extrapolation of the scaling law doesn't account for potentially saturating losses, right? So perhaps this just tapers off and doesn't hit this star point. And hey, that is a legitimate concern, but we have seen Transformer++ go up to 70 billion parameter scales. That's Llama 2. So we're hopeful that this will kind of keep going up. Right now, we are talking to a few people to try and get more resources, get more GPUs to make this happen, because we're a relatively small academic lab that are very much GPU limited. Another thing that is worth noting is that flops, the nomenclature of flops is true for the transformer plus plus case, but we're counting ternary operations in our approach as a flop as well. So in a way, each unit of computation that our model reports is already a lot cheaper than what transformer plus plus can achieve here. So I mean, if you were to normalize this to like energy for a flop or a ternary operation, then that would kind of set our map-mole-free LM approach far more to the left. So we'd get far smaller losses for far less compute. So that's what I want to say about the scaling law. With that being said, let's go into some of the results that we achieved. On this side, we see the zero-shot accuracy of our model versus transformer plus plus on a set of benchmark data sets. I guess as your model scale gets larger, so in the top cluster, we have the 370 million parameter model. On the bottom cluster, we have the 2.7 billion parameter model. We list out the number of training tokens, the number of blocks, and the embedding dimensions. And as the parameter scale increases, as I mentioned before from the scaling law, we're now quantitatively seeing the gap between transformer plus plus and map-mole-free also decreasing. Some things worth noticing here, I guess, is that this WGE Winogrand, this is a binary choice question, and the ARC challenge is a 4-choice question. So in those cases, in those two benchmarks, it's kind of like a coin flip or a 4-sided coin flip anyway, and doesn't quite reflect what I'm saying here, but we included it anyway because it is a standard benchmark. I also want to flag, if you were to screenshot this and go ahead and compare it against other similarly sized models, one thing that you need to account for is how many training tokens were used. So Gemma, for example, that was trained on 6 trillion tokens. Llama 3 was on 15 trillion tokens. Again, our resources in a small academic lab limited us to far, far smaller tokens, to 100 billion tokens. So if we wanted to scale up to 15 trillion, I will more than gladly accept donations for $1 million to make that happen. Now, we're relying on GPUs to train these models. Of course, there's a set of gradient operations that need to be overridden, in that if I was to ternarize a full precision weight, then I need some sort of quantization-aware training using straight-through estimators. So I'm not going to go into the low-level detail of the non-differentiability of ternary operators, but so ultimately, you need GPUs to train these models. But then inference can go GPU-free, and if we want to test out something that really milks ternary operations, then what do you want to look at? Custom hardware. And so if we want to meet the NeurIPS deadline, then we have 3 weeks to make this happen. We wrote this all up in System Verilog RTL, so it's thoroughly, all the results that were in the preprint are thoroughly unoptimized. There's no DSP, so we're not milking the kind of tailored acceleration components on an FPGA, where there's no DDR bursting, there's no pipelining. We wrote a custom assembler for our custom instruction set, which was used to convert assembly files into an instruction ROM. And that instruction set included all the ternary operations that we needed. So if I was to kind of test performance across different embedding dimensions, so sweeping across D for different model sizes, then perhaps in a more interpretable set of numbers. So I mean, we've got runtime and projected runtime. If we were to access more values from DDR, and energy power estimates from power profiling tools, in a more interpretable set of numbers, what we're getting is 23.8 tokens per second at 13 watts. In contrast, the brain operates at 5 to 15 tokens per second at approximately 20 watts. That's what it takes for me to talk about map-mole-free through StreamYard. Again, there's no pipelining, no batching, so there is a lot of room for improvement here. This is, I really want to stress that this is thoroughly unoptimized. And so next, we also evaluated resource utilization. We tested the use of various core counts. And what I want to highlight here is the latency. So if you consider this latency of the core itself versus DDR, so we're showing that memory access is not the bottleneck, which is typically going to be the bottleneck in most of your neural network workloads. So at the moment, it turns out that the 3 required ternary accumulations, and in the paper we do call it a ternary map mole, those instructions take up nearly all of the total execution time. So in future work, if we were to introduce parallelism and caching to improve the ternary map mole execution time, then that could lead to a huge change in the balance between core and DDR latency. With all of that being said, I'm just going to kind of fly through a bit of a future vision of where I hope these models are going to go. But let's say that I have conventional self-attention on some hardware where we've got inputs streaming into some accelerator, and then we've got outputs coming in. Given the large KV cache that is needed, so I mean, how many H100 GPUs do I need to serve one single user at 8-bit floating point at a throughput that matches human reading speed? So a semi-wiki estimate was 256 GPUs. Now, how many daily visits does ChatGPT get? There was some number that said 1.75 billion at its peak. Of course, that disaggregates somewhat. Now, this kind of darkening of the inference fabric just indicates that you're fully utilizing all of the hardware that you have available to you, right? Now, if instead we go into the direction of alternative models, so the precursor to this MapMole-free paper was this Spike GPT model, which had some temporal sparsity and used state space approaches, etc. We released it about a year before our MapMole-free work. Now, if I was to take some sort of temporally sparse, time-varying self-attention mechanism, and the idea is this. I mean, if you have sparsity in weights or in your data flow, then you might not need to have to fully utilize all of your hardware. So you can kind of run parallel workloads concurrently. You can basically do this multi-tenanting where many users can execute on the same hardware. So SNNs refers to spiking neural networks. It's a big part of the work that we do in our lab, where you just have neural networks with a high level of temporal activation sparsity. In that case, you're only accessing data that needs to be accessed, so you have less data movement but low utilization. And hardware engineers and silicon guys, they hate to see low utilization. They don't want things there that aren't being used. So if we combine that with some sort of vertical cache or some memory that's stacked on top, then you're able to concurrently access all of your data that needs to be accessed. And so you end up getting energy benefits that are massive as a result of this parallelism. So with that being said, I kind of see that MapMole-free could enable huge concurrency on the same hardware, especially if we were to push this towards some sort of temporally sparse neural network. This work was led by Rijie Zhu over in the back here. He did an incredible job kind of seeing this to fruition, and a lot of sleepless nights. There's a fantastic quote that the next greatest advance in neural networks is not going to be from some large, incredibly well-funded company, but rather from a grad student. And so I don't know, I couldn't help but think of that quote when Rijie was blasting out these results. It's really quite cool to see him doing so well. And of course, got to say thank you to the lab that actually makes this work possible. So with that being said, thanks very much. Forgive my 17th of June typo. And the wrong title. I'm clearly sleep deprived on this, but yeah, thanks a lot.
Oh wow, that was like really interesting. At least for me, and I had a bunch of questions I wanted to ask, but like primarily, I want to know like you mentioned a lot of custom hardware stuff. Is it possible to leverage like not generic? Kind of doesn't really make sense, but is it possible to leverage like other NVIDIA type hardware, AMD type like GPUs, or is this something that's going to be kind of limited in terms of distribution because it needs some sort of like custom hardware implementation?
Yeah, no, that's a really important question. In terms of training, no, we're stuck with GPUs. This is, of course, a model that's targeting inference. Now, for inference, if you want to be able to exploit GPU acceleration, now the limits of what we've really done here is fusing the operations at the CUDA or Triton level in order to accelerate inference. Now, if you want to push that a little bit further, then we would be relying on ternary kernels. And I believe that they They might exist. I'm not sure if they exist. When I kind of looked it up, they seemed a little primitive and a bit janky, and I couldn't really figure out how to take advantage of it myself. But if you start seeing more mature ternary kernels that can take advantage of 8-bit widths, 8-bit addresses and whatnot, then you're able to take more advantage of GPUs. I would say that the advantage that you can take of GPUs, even with ternary kernels, is going to kind of be there is going to be a ceiling on that custom hardware can blast through. Technically, a ternary bit still needs 2 bits, right? So you're kind of not using, if you have 3 levels, then you need 2 bits. You need 4 levels to store that. So you're not taking full advantage of, I guess, your SRAM or whatever memory that you're using. So custom hardware does have some opportunity to just push past what GPUs can do. That is not to say GPUs are useless here. They are still very much able to take advantage of this.
Okay. What about CPUs?
Oof. I guess so, yeah. They just do it far slower. So I think everything I said does generalize to CPUs. It'd just be like taking something super slow and making it slow.
Okay, cool. Thank you, Jason.